Our project was focused on parallelizing Dijkstra's algorithm using OpenMP. The goal is to improve the performance on multi-core CPUs by exploiting shared memory parallelism. Why Dijkstra's algorithm? We used it because it's widely used in applications like GPS routing and network optimization. However, it's sequential, so it's very slow. But in our experiments, running on 10,000 vertices took about 6.4 seconds, which confirms its OV squared time. Our goals of the project was to implement a parallel OpenMP version, compare it to the sequential baseline, and address race conditions correctly. We evaluate execution time, scalability, and synchronization overhead.
This slide shows the performance of the sequential version, which we use as our baseline. We tested the graphs with sizes ranging from small inputs up to 10,000 vertices. As the graph size increased, the execution time increased as well. For the largest graph, the execution time reached approximately 6.43 seconds, which clearly demonstrate the exponential time complexity of the sequential algorithm. These results confirm that sequential implementation does not scale well for large graphs and motivates the need for parallelization.
This slide shows where race conditions appear in the code. In the first part, multiple threads try to select the minimum vertex by updating main.dist and U at the same time. In the second part, during the relaxation step, multiple threads may update dist v at the same time. These concurrent updates cause race conditions and can lead to incorrect result.
Tested OpenMP synchronization methods. With no synchronization, it was the fastest, but it was incorrect. After that, we did the critical, which was correct and added performance balance. Then we have the atomic, which is good for single variable updates. It was correct, but it was slower. Then for the reduction, this was very slow and incompatible with Dijkstra, and reduction showed the lowest overhead compared to the critical and atomic.
This slide presents the experimental results of our OpenMP implementation. The critical synchronization method performed best because it protects a small code section, resulting in lower overhead and correct execution. It achieved the lowest execution time compared to other methods. However, no significant speed up was observed beyond 2 threads, as bottlenecks dominate and the difference between results are small.
Speedup was limited. Amdahl's law serial minimum selection dominates, high synchronization overhead, shared memory contention, graph size too small for meaningful parallel gains. Most papers test the huge graphs or GPU clusters, but we tested practical laptop scale graphs where overheads dominate, threads fight for shared memory, correctness becomes a real issue. Our work provides a realistic insight into OpenMP limitations. Our findings confirm literature by He 2021. OpenMP gives only modest improvement due to synchronization overhead.
To conclude, parallelizing Dijkstra with OpenMP is possible, but it results in limited speedup due to synchronization overhead. For small graphs, this overhead dominates, making the speedup very small. The critical directive is the most reliable synchronization method because it ensures correctness and prevents race conditions. Overall, standard Dijkstra is not scalable on shared memory CPUs, and real performance gains require algorithm-level redesign rather than simple parallelization. Thank you for watching.